Hello everybody, good afternoon. Any questions? Any questions? No questions? No questions? Okay. So we are basically done with the relativistic formulation of Maxwell's equations. Um, I haven't worked out on the board yet how you get Maxwell's equations from the Faraday-Maxwell tensor. I think I believe that we could do as an exercise. Um, it is also, you can find literally hundreds of resources for that. It's just straightforward taking derivatives. That's all you have to do. So now there are some topics that in relativity which I did not cover. Some of those topics are, one is about paradoxes. There are several thought experiments in special relativity which appear to give paradoxical answers. Right? So a paradox is something which is logically inconsistent. So of course they are not paradoxes if you look at them from a relativistic perspective. So I'd like to cover some of those. There is the twin paradox, then there is the what is known as the horse and barn paradox, or also known as the train and bridge paradox. And then there is the question of rotational motion in relativity. That is also something that I want to cover. So apart from this, going forwards, the topics that are remaining. So there is electromagnetic radiation, obviously. Then linear Decker potentials, which is these retarded relativistic potentials of moving point charges. Then there is Thomas precession, right? So you don't really need relativistic, this electromagnetism talk about Thomas precession, but the relevance of Thomas precession becomes clear in the context of when one looks at the Hamiltonian of what is known as spin orbital. So that brings me to the topic after radiation, which is the Lagrangian and Hamiltonian formulation of electromagnetism. So the Hamiltonian picture, right, is obviously needed because if you want to do physics in the presence of electromagnetic fields, you have to understand, right? I mean, how do you do physics? You do physics with Hamiltonians, right? Or Lagrangians, either way. So we have to know how to write down the Lagrangian or Hamiltonian of both the electromagnetic field on its own and also coupled to point particles, charged particles. Right? So if you, and then those, the resulting Hamiltonians, they have classical solutions. Then one can also do quantum physics, right? So that is what leads one into what is known as quantum electrodynamics, right? Doing when you start to look at the properties of radiation coupled to matter. So, of course, we won't be studying anything about quantum electrodynamics, but as far as Hamiltonians are concerned, so I will be talking about up till the point that you get this spin orbit coupling and other different phenomena. So, so first there is radiation. Now the thing is, which topic should I do first? Are there any opinions as to whether I should talk about radiation first or about the Hamiltonian and Lagrangian first? How many people for radiation? How many people for Hamiltonian? Okay, so radiation it is. So we will do the Hamiltonian part first. Okay. Uh, all right. So uh, and then in between at some point I'll come back to the remaining topics which I mentioned, which are the relativistic paradoxes, rotational motion, and then there are a couple of other topics in relativity. It turns out that this book, Steve's book, who suggested it to me? Akshay? Last semester somebody huh? Anandu. It is one of the best textbooks I've ever seen on any topic. There is so much history and humor and observations and physics that is to be found in that one text. It is just amazing. So yeah, so there are many things that I'm learning just by reading. So there, we'll come to those topics later. Okay, so for now, let me come to the Hamiltonian and Lagrangian populations of electromagnetism. Okay, so there are the references are, well, you have Steen's textbook, chapter 8. Chapter 8 is on radiation. Chapter 8 is electromagnetic radiation. I think chapter 16 or something like that is. Yeah, chapter 14 is the Hamiltonian. Okay. In between, of course, there are many chapters in Steen that we are not going to talk much about, but which are important. So, um, but we have a limited amount of time. We can't cover everything. Okay. So let me start with this Lagrangian formula. Right? So now you have all studied Lagrangian mechanics, I think, right? What is the statement of Lagrangian mechanics? So essentially, it is an application of what is known as the relational principle to solving physical problems. Okay, and when you first learn about Lagrangian mechanics, at least when I first learned about it and I saw this relational principle, I thought it was something magical almost, right? Because the idea is that you don't know what the equations of motion of a system are, right? You start with something, some mysterious quantity that is called an action, right? Now, the form of the action also is something that is not known a priori, but it is something that one can guess based on the symmetries of the problem. So if you have a certain system and there are some dynamical variables and some fields and there's some configuration space, you can write down the what the action should be based purely on some very general on considerations regarding symmetry, right? So for instance, if your system is translationally invariant, your action should also be translationally invariant. Um, then your action should be um, so so the act so that limits the possible choices of the action. Okay, and so in a way, what you're using is what is known as Occam's razor, right? So if you've heard of Occam's razor, anybody's heard of Occam's razor? It's the latest in shaving technology. Uh, no? So, William of Ockham, somebody like that, last name was Ockham, right? So, he's a British fellow, long time back, many centuries back. And so, he basically put forward this hypothesis that the simplest solution is generally, not always, but most often, the simplest solution is the best, or the simplest explanation is the best, right? So when you have like some set of circumstances, whether it's physics or whether it's could be anything, right? Could be some event that happens in society, for example, right? Like for example, 9/11, right? Now there are a lot of like theories that this was a conspiracy and all this. Remember 9/11 when you all were still like right? So, but if you think about all of those theories, they require such complicated explanations, right? Because if you say that this was some conspiracy to bring down these towers and all this, you have to come up with so many different things that must have happened for this to be a conspiracy, right? So to go from point A to point B, you have to like come up with so many different options. And now when you start thinking in terms of probability, let's say, what is the probability that each one of these steps could have been carried out successfully and also without anybody learning about it, right? And then you multiply the probability for this step and this step and this step and this step and this step, right? Because they all have to be carried out successfully and they all have to be done in complete secret. And then you start to realize that it just becomes, it is not ruled out, right? It is not ruled out, but it just becomes overwhelmingly unlikely. As opposed to the simplest explanation, right? Which doesn't involve any conspiracies. Well, there was a conspiracy. There were some people who planned to do something very bad. So, in the language of variational calculus, right? Or also there is another word that is used, which is optimization. It's used in engineering and production, engineering and applied branches of physics. So what this general idea tells us is that it is much more likely for the system, whatever the system is, to take the shortest path between any two points. Right? Now, the system can take a longer path, right? But it is becomes less and less likely to do so the longer the path becomes, right? So you need what you need to do to in order to give this picture a mathematical formulation. First of all, you need a notion of distance, right? You need a notion of distance between two different configurations of your system. Okay. Then the second thing is uh, you need to understand how to do this variation, right? So you have a certain path. This is my original path. This straight line. Let's say gamma, right? And this gamma. So I'm talking about a particle. So which starts off at some coordinates t and x, right? And it ends up at some coordinates t prime and x prime, and in between it follows some path, okay? And this path is gamma and x mu. It's a function of uh, so there is some path and it has some coordinates x mu, which is p will be some function of gamma, where gamma is a parameter. Let's say gamma is 0 at the beginning and 1 at the end. So then you have four different functions: x of gamma, y of gamma, and z of gamma. Right? So you have these four functions. The choice of these four functions defines the trajectory which begins at your initial point and ends at your final point. Okay. So now you want to talk about optimizing something, right? Optimizing some quantity. What quantity should you optimize? So it turns out that the quantity that is, you know, which makes sense. Why it makes sense is another problem. Okay, that is something that we are still in the process of understanding. It is not something that has been understood completely. Okay? So, and that quantity is this something called the action, right? And for a point particle, this action takes the form of the kinetic energy minus the potential energy. Okay? So what you can do is, uh, so this quantity defines the Lagrangian, and if I take the Lagrangian and integrate it over the whole path, now the path goes from 0 to 1, so I use gamma as my parameter, and this is my action. And this action is the associated weight of this path. Okay? And if you want to talk in terms of, let's say, probability, then what happens is that this same picture can be taken into statistical mechanics, it can be taken into field theory, right? And there, what you say is that there is a certain probability associated with the given path, and that probability is e to the minus s by h bar. Weight means, like for any given, for a different path, I will have a different weight, right? This weight is what I'm minimizing, right? So when I'm extremizing my action, so I'm trying to find the path which has the least weight. Okay. So these days in high energy physics, people are looking at this from the perspective of quantum information, and they are viewing any such process as some sort of a quantum circuit which is taking some state and evolving it to give you the final state, then the trajectory has some sort of complexity associated with it. Complexity has to do with how many operations are performed. So there is this emerging notion of complexity associated, that action measures complexity. But again, you know, these are all like topics, ideas that are still very much in development. Okay? For our purposes, right, what we want to do is we want to understand how to use this. Right? So now, let us look at the action of a point particle, for instance. A point particle satisfies this equation of motion, right, Newton's second law. And this can also be expressed alternatively as minus the gradient of some potential is equal to dp dt, can be written as dx dot dt, right? So now we associate this function which is called the Lagrangian, which is t minus v with the particle. Okay? Now the equation of motion, this is the equation of motion, right? What is this Lagrangian? Well, there is some kinetic energy that you associate with the particle, that is 1/2 mv square, right? And then there is some potential energy. Well, that potential energy is just minus v. Whatever that function v is, v can be anything. It can be a harmonic oscillator, it can be a Coulomb potential, right? It can be like any function of the coordinates. It can even be time dependent. Now, this Lagrangian contains hidden within this expression, the equation of motion, right? So what we do is we write down the action as integral of this Lagrangian and integrated from the initial starting point to the ending point. And here I have written things in terms of some parameter gamma, right? You can always take this parameter gamma to be equal to the time, right? So this is the more general way to write it. If you just set gamma to be equal to the time as measured by some observer in their frame of reference, then this becomes, the Lagrangian becomes a function of t, and then x becomes a function of t, y becomes a function of t, z becomes a function of t, right, times dt. The advantage of this sort of formulation is that it lends itself more easily to the relativistic setting. When you want to look at the action for a particle, which is a relativistic particle, right? You don't want to pick out a preferred time or a preferred sense of space, right? So in that case, this formulation is better. Okay? And now, when we try to extremize this action, right, we end up with a certain set of equations. And how do we extremize this action? Well, L, it is a function of the coordinates and the velocities, right? X and x dot. And if there is more than one particle, then you will have some index here, right? Where I will go from 1 to the number of particles. And so then we perform this. This is a very standard problem, right? I'm sure everybody has worked this out at some point, how to do the deviation, and we are left with a set of equations which tell us what the form of the path should be for which this action is extremized. Okay, so note that I'm not using the word either minimum or maximum. I'm using the word extremum. Right. So an extremum is some path. So if you have some function, an extremum is the point at which the derivative of this function vanishes. Right. But because the derivative of that function vanishes, that doesn't mean that that point is a minimum. It can also be a maximum. It can also be a point of inflection. So to check that it is indeed a minimum, what you have to do, you have to find the second derivative, right? And if it's a minimum, then what will happen? The second derivative has to be positive, right? So we will not worry too much about these issues. Okay? Everybody knows. You have all seen this, right? I know you write this. So now this quantity, the partial derivative of the action with respect to the ith velocity, right? What is this? This is referred to as the momentum. It is called and it's called generalized momentum, right? Why is it generalized? Well, you are familiar with the usual notion of momentum in this form, right? The mechanical momentum. But this is true, this is the form of the momentum for linear motion. Now you can have all different kinds of motion. You can have rotational motion, right? If you have a rotational motion, what is your configuration variable? It's the angle, right? And the associated velocity is the angular velocity, right? In that case, your generalized momentum becomes the angular momentum, right? It has different units. So, okay, so we have this momentum. Now, what we can do is we can perform a change of coordinates. So what we have to begin with is we have something that is known as configuration space. Okay? So the configuration space tells you the state of the system at any given instant of time. So it is the collection of all the positions and the velocities at a given time t. Okay? So, and if you want to ask what is the dimensionality of this space, so let's say you're looking at a single point particle in 3 dimensions, or let's say 1 dimension, that's easy. So in 1 dimension, how many independent, well you only have one direction, so your position variable takes values in r, and your velocity is also a real valued function, and there is only one component, so you get r square, right? So if you have n dimensions, then what happens? For each independent dimension, you get one velocity and one position. So you get 2 times d, right? And now if you have n particles, then each particle has an independent copy of this. So this gives you r times 2 to the 2n times d.
So this is phase space.
Yes, I was not sure about that. This is space. Configuration space is when you consider only the positions. So this is phase space. Now, so if you have a one particle in 3 dimensions, then your phase space is 6 dimensions. 6 dimension. Okay. Now, in this space, we can perform a change of coordinates, okay, which involves replacing these velocities with these momenta, with these functions, okay. And how do we perform this change of variables? We perform it using something known as a Legendre transform. Okay. Now, a Legendre transform is a very general uh, tool. Okay. It has nothing to do in particular with Lagrangian or Hamiltonian mechanics. Right. Legendre transform is also used, for example, in thermodynamics. Right. When you want to talk about the different kinds of thermodynamic potentials, you have the Gibbs potential, Helmholtz potential, right, and so on. So there your phase space, for instance, is described in terms of, let's say, pressure, volume, and number, right? And you want to switch to a different description in terms of, let's say, pressure, volume, and entropy, right? Or pressure, volume, and temperature. Then what you do is you perform a Legendre transform, right? And what is this Legendre transform? I take my Lagrangian, which is a function of my positions and my coordinates, right? And I want to write down a function which depends instead on this momentum. So what do? I take, well, this is the form of the Lagrange transform. P xi dot minus, and here there will be a sum over I, and this resulting function is a function of the momentum and the coordinates. Okay. Now, right now one can see how this works. If you take this partial derivative of L with respect to xi, you get pi, right? So let's say I do this with h. I take partial derivative of h with respect to xi dot. What do I get here? I get pi, and here what do I get? Here also I get pi. Okay, 0. So this new function h, right? Even though it is written, it seems that it will have some dependence on this expression xi dot, because of the fact that this momentum is defined in this way, right? Because of that fact, this expression Hamiltonian turns out to not have any dependence on the velocity. It only depends on the momentum. Right? Now, anyway, these are all standard concepts of mechanics that you have all studied before. And in this framework, now one can again write down what the equation of motion should be. And the equation of motion take this form: dh by d pi is equal to xi naught, and dh by d xi is equal to minus pi naught. Okay, so these are my Hamiltonian equation of motion, right? And the Lagrangian, as I mentioned earlier, is this quantity t minus v. And if you look at systems which are conservative, right? So conservative system is something for which uh, the work done by moving a particle from one point to another, or for moving the system from one configuration to another configuration, does not depend on the path it takes through the configuration space. Such systems are called conservative. For such systems, the Hamiltonian will turn out to be the sum of the kinetic and the potential terms. Okay? So this is the basic technology of variational calculus, right? So now, initially when the Lagrangian was developed by Lagrange and when Hamiltonian was developed by Hamilton, uh, they obviously did not know of quantum mechanics, right? They were simply looking for alternative formulations of the equations of laws of motion, right? Uh, so I suppose the motivation must have been the same, that idea that I said in the beginning, that the Newton's equations of motion, it's as if they appear out of nowhere magically, right? So I suppose the motivation must have been, in the case of, let's say, Lagrange, that, well, there is this nice, beautiful technology of variational calculus. Can I apply this variational problem to mechanics? Right? That's one motivation. Another motivation might be to better understand why these equations of motion take the form that they do. And then Hamilton's motivation was to come up with a sort of a picture in which uh, there was a certain symmetry between the coordinates and their rate of change, right? So if you look at the equation of motion, coordinates and velocities are not treated on the same footing, right? But when you make the change to Hamiltonian mechanics and you write things in terms of positions and momentum, now when you look at these equations, right, then if you did not know beforehand which was which, right, you would not be able to say, okay, this should be the position and this should be the moment, right? There is a symmetry here, right? So the symmetry is that I can send x to uh, x to p and p to minus x, right? So I have this symmetry. And then what makes Hamilton's formalism nice is that it can be applied, for instance, in statistical mechanics, right? When you want to find what should be the Boltzmann weight of a given configuration, say that, well, that Boltzmann weight is given by the Hamiltonian, right? And of course, ultimately, it turned out that to do quantum mechanics, you need the Hamiltonian and the Lagrangian formulas, right? Because it is the Hamiltonian that you know you think of as an operator, right? And and that allows you to construct your quantum state space and the evolution operator, the Schrodinger equation. And the Lagrangian is what you use in order to do path integrals. So without the Lagrangian, you can't do field theory. Now, so of course we are not interested in field theory, but we are interested in quantum mechanics. And more importantly, we are interested in relativistic quantum mechanics. But before that, let us look at the Lagrangian of a free particle. Okay? Now, if you were talking about a non-relativistic free particle, the Lagrangian would just be 1 half m x dot square, right? But we want to work out everything in the relativistic framework, right? Is this expression relativistically viable? Is this relativistically, is it invariant? No, right? So, here, this is where the first application of symmetry comes into the picture. Okay? So, what is the symmetry of space-time? Lorentz invariance. So, if I want to write down a Lagrangian or an action, right? Then I should take something, some quantity, which is a Lorentzian scalar, which is invariant under Lorentz transformation, right? Now, if I have a particle, a single point particle, it's moving from point to point. What is the invariant quantity that I associate with this particle, with its motion? Space-time is the everything. I'm talking about the particle's trajectory. There's a particle that is moving from point to point. Okay. There is now, if I look at this trajectory from the frame of reference of a different observer, right? I'll see that it has different coordinates and momentum. But there is something which remains invariant. What is that something? Space-time interval. Is that what you said initially? I missed the interval part. I'm sorry. The space-time interval, right? So a particle that moves along any trajectory, and now that parameterized version of the trajectory is useful. Okay, so I'll write down the coordinates of the particle as a function of this parameter gamma. All right, and so at some value of gamma, the location of the particle is at x mu. At in the next step, right, the particle has gone from to the next small infinitesimal parameter change, gamma plus, right, and the associated space-time interval is this quantity, right, just the difference, and with this quantity I can associate ds squared, and what is ds squared? It is just dx mu dx mu, right? The length of this space-time interval.